Hello everyone and welcome back. Now, in the previous video, we talked about how to solve non-homogeneous equations, and in particular, we used the method of undetermined coefficients. Now, it's excellent. It's a great method. I personally really love it because I don't think it's that complex and it gives us solutions to differential equations. But as you know, it's extremely limited. We can only handle right-hand sides that maybe are exponentials or polynomials or sines and cosines, right? And a lot of functions just aren't those functions. So if we remember what we did for second order equations, we gave an update to that method and we called it variation of parameters. And that allowed us to solve non-homogeneous equations with more intricate or complex right-hand sides. What we're going to do in this video is we're going to update that method for higher order differential equations. So let's go ahead and get right into it. Let's imagine we are given, we're going to use our L of y notation here. Remember, we use this to denote differential equations. In this case, it's an nth order differential equation. We got rid of the coefficient in front of the highest derivative. Remember, we've seen this before. And now we have P1 of t, yn minus 1, all the way down until we get to Pn minus 1 of t times y prime plus Pn of t times y. That's my L of y. And of course, today we are going to talk about non-homogeneous equations. So we imagine there's a g tacked on the end there. Okay, let's go a little further. Let's imagine we already have access to the homogeneous solution. So I call it YH. And we remember this is an nth order equation. That means that from the Wronskian, there's n linearly independent solutions here. So let's denote them as Y1, Y2, Y3, all the way up to Yn. Okay? So this is all stuff that we've seen before. And now if you think back to what we did with variation of parameters for second order equations, we let the c's basically vary with respect to the independent variable, in our case, t. We're going to do exactly the same thing, right? So you could probably guess a lot of the content of this lecture just based on what we did for second order equations. Again, all we're doing is updating. So here, follow me. Let's go ahead and set capital Y of t, the specific solution, to be u1 of t, y1 of t, u2 of t, y2 of t, all the way up till you get un of t, yn of t. Okay? So we're going to put this into the differential equation, right? This is exactly what we do. So that requires me to take some derivatives. Now, this is just going to be tedious to write out, but let's go ahead and write it out. Now, these are all products. So let me write I'm going to do the derivative, but I'm going to skip a step and I'm going to clean it up. Okay, so let's do u1 times y1 prime. That's from doing the product rule. And I'm going to put all of the yn primes in one bracket. Okay? And then I'm going to put all the u primes in another bracket on their own. So if you take a look at what I've done here, I have the full product rule represented, right? u1 times y1 prime, u1 prime times y1. All I did is I separated them out. I said all the y derivatives on the left, all of the u derivatives on the right. That's all that I wanted to do. And why is it that I wanted to do that? Well, again, if you think back to what we did with separation of variables before, we're going to set this to 0. So this looks a lot like what we did with variation of parameters for second order equations, right? If you put n equal to 2, this gives you exactly the same condition that we had previously. Okay, so then let's do it again. So again, well, in this case now, I get a second derivative. This piece is 0, so all I'm doing is taking a derivative right here. And again, I'm going to do the same little trick. I'm going to separate out by y derivatives and u derivatives. So u1, y1 double prime now, all the way up to un, yn double prime. And then, now taking the u derivatives, I get u1 prime, y1 prime, plus all the way up, un prime, yn prime. Now, even though these look similar, they are very different conditions. This one is in terms of the y's. This one is in terms of the derivatives of y's. But I'm going to play the same game. I'm going to do this. I'm going to say set to 0. Okay, so now I have two conditions already. And basically, you're going to keep doing this, right? So my words of encouragement, keep going. Keep doing this. Keep taking derivatives and keep setting this right-hand piece equal to 0, okay? So eventually, you are going to, so this implies that every time you set this thing equal to 0, you're going to get this condition, okay? u1 prime, y1, and then I'm going to use m as my sort of counting parameter here. So the m minus first derivative of y1 all the way up, un prime, yn, m minus 1. I'm going to set all of those equal to 0. And this is going to happen for all m equal to 1. So when m is equal to 1, these are zeroth derivatives. They're the original functions. That's condition 1 right here. When m is equal to 2, all of these are first derivatives. That's condition 2 right here. I want you to keep going all the way up to 1 less than the order of this differential equation. And again, this is abstract for now. It's going to make a lot more sense once we get to an actual example. Okay, so bear with me for the abstraction. It becomes much clearer when you have hard numbers to put into this. And so what happens here is that this gives, well, this gives what? This gives your capital Y of t, if you go take all of these derivatives, these mth derivatives, well, the first time you did it, you got this piece right here only because we set this to 0. Second time you did it, you got this piece right here only because we set this equal to 0. And in general, what you're going to get is u1, y1, the mth derivative. That's why I had to have these m minus 1s. That might have been confusing. And then all the way up, un, yn to the m. Again, for all m from 1, 2, all the way up to n minus 1. So I'm going to do something, but you put all of these, so put all ym of t into L of y. Basically what you get is you get a u1 times every single derivative of y1. But since y1 is a solution of the homogeneous equation, poof, that disappears, right? You factor out the u1 and you get L of y1 equal to 0. So what are you left with after doing all of this? The only thing that you are left with is the highest derivative term, which was not a condition that we set to 0, right? This only goes up to n minus 1. So this actually gives you u1 prime y1, the nth derivative, the n minus first derivative, pardon me. And then all the way up, right? So it's the equivalent of this condition that was left out, plus un prime yn to the n, or the n minus first derivative. And because it's L of y equal to g, this thing is equal to g. So this gives you a lot of equations that you can solve. So let's take a look at what it all gives us. Equation 1 gives us u1 y1 prime all the way up, un yn prime. This is equal to 0. first thing that I said. The second equation gives me u1, y1 double prime all the way up, un, yn double prime is equal to 0. Again, that's my second equation. Third equation will be the third derivative. All the way up, you use all of these right here until you get to the very last one. So your nth equation here, your nth equation is going to be this one that's hanging off the edge. The last thing that you didn't take care of, the piece that actually comes from the differential equation. Remember, you assumed all these all the way up. This is the only one that actually fits the differential equation. So let's look at that one. This is going to give me, sorry, these are all primes on this. This is going to give me u1 prime, y1, and then the n minus first derivative, plus un prime, yn, and the n minus first derivative. And this is equal to g. Now, what I want you to notice there is this is now n equations. N's just a number, so don't get lost in the abstraction here. It's now n equations in n unknowns. Those unknowns are the derivatives of u1, u2, all the way up to un. Also, take a look at what the first column of that matrix would look like if you put this into a matrix form. y1 prime, y1 double prime, or sorry, this is y1, pardon me, and this is y1 prime. This makes more sense. All right, so y1, y1 prime, all the way up to the n minus first derivative of y1. Where have we seen that before? We saw that in the computation of the Wronskian. So everything is sort of wrapped into one here. It's very, very similar to what we saw for second order equations. It's just much larger. And in fact, we can write down the explicit solution to this differential equation, or to this linear equation. Okay, so I'm going to spare you the gory details of this. And I'm going to say this comes from Cramer's rule. So Cramer's rule is a method from linear algebra for solving these big linear systems. And in fact, we can actually show that the derivative of each one of these u terms, so I'm using m as my index that runs along these, is equal to g of t, and then wm of t, I'll explain what that is in a moment, divided by w of t. Okay, so what are these things that I have on here actually? Well, w of t, that's my Wronskian. Now, what is the Wronskian in this case? It's the determinant of the linear matrix that you have created, right? This is a system of linear equations, ax equal to b or something like that. The Wronskian is the determinant of that thing. Now, what is wm? Well, again, this is coming from Cramer's rule. So this is the Wronskian. So again, it's a kind of Wronskian, but it's a little funky. And it's formed by replacing, now it's formed by replacing the mth column, so in your usual Wronskian, by this thing. So I'm going to write it as a column or as a row vector. It's all zeros except a 1 in the bottom row. And so what all of this gives you, when you wrap it all back up, this says that therefore the specific part of y, that's where we started with this, well, this is equal to the sum of m equal to 1 to n, that's my indices that I'm running over here, of ym of t, and then times, so all I need to do is integrate this thing. I'm going to use an indefinite integral to say antiderivative. That's all that we're using here. And then it's the antiderivative of this, g of s wm of s divided by w of s ds. I'm just using s here as the integration variable to just really highlight what's inside of this, right? But really this just means antiderivative, okay? So I don't want to get too hung up on the notation here. but I do want you to see what's going on. Okay, so this, I mean, we've got a formula, so it's not terrible, but it's still a little fuzzy, right? It feels very, very abstract. It feels a little intangible at the moment. So let's go ahead and get ourselves into an example here, okay? Let's take a look at this one. Here's my example. Let's do, I'm going to actually use a general right-hand side. So y double prime minus y prime plus y. I'm just going to call the right-hand side g, okay? So basically, at the end of this, I'm just going to show you how you can arrive at these equations based on what I have for the left-hand side of this. So you could just plug and play any g you want in here. You want to put sec of t in here. You want to put tan of t. You want to put t to the 200. You want to put t to the 100 times cos of t. You know, I mean, that one could be handled with the previous example, but that's okay. You can do all of them with these straight integrations. So first of all, this gives us, if you solve the homogeneous equation, so all you need to do is find the characteristic equation, find the roots. I get e to the t, and I get a repeated root, so I get t e to the t. And then the last one is e to the minus t. Okay, so I have three linearly independent solutions. First thing I want to do is I want to compute the Wronskian, because the Wronskian is used at every corner of this application. So the Wronskian of t, I'm going to use the straight bar to denote that this is a determinant that's being taken here. But the first piece is y1, and then y1 prime, and then y1 double prime, and then y2, and then y2 prime, and then y2 double prime. Right? So I'm going all the way up to the n minus first derivative. In my case, n is equal to 3 here. Okay? Last piece, e to the minus t, minus e to the minus t, and e to the minus t. Now, everything's got an e to the t in it. So what I could do is I could factor out an e to the t from the first column. That means that the derivative will be multiplied by e to the t once I factor it out of just the first column. Then I could factor that e to the t out of the second column. That means that the derivative after factoring will be multiplied by e to the t. Then I can factor out an e to the minus t from this third column. So I get 1, 1, 1, t, t plus 1, t plus 2, and I get 1 minus 1, 1. Okay, so what happened? Pulled out the e to the t from the first column, pulled out e to the t from the second column, pulled out e to the minus t from the third column. These two together cancel each other out. And so this thing is just being multiplied by e to the t. And I'm going to leave you to have a little bit of fun here. Maybe you might have to refresh yourself on how to compute determinants. But nonetheless, you can very easily identify that the determinant of this thing is equal to 4. So it's interesting. It's independent of t. And so I get 4 and then times e to the t. Go ahead and try that, right? Pause the video, see what you can get. Okay. Well, that means we've got the Wronskian that shows up in the bottom here. Remember, we always want the Wronskian non-zero. Here we can kind of see why that non-zero term is coming in, all right? We can't divide by 0. Okay, let's take a look at WMs now. Okay, so let's look at W1 first. Now, how do you form W1? Well, it says right here what we do is we take the first column. Oh, I forgot to put column here. Pardon me. I'm sorry if that was confusing. The first column by 0, 0, 1. Okay, so that means 0, 0, 1. And then the rest of it stays as is. E to the t, 1 plus t, e to the t, and t plus 2, e to the t, and then e to the minus t, minus e to the minus t, and e to the minus t. Okay. Now, what you can do is you can compute determinants. Now, the nice thing about this first row is it means the determinants are pretty easy to compute, right? Because you remember 3 by 3 determinants, 4 by 4 determinants, all of these higher determinants, they're a little bit more complex than 2 by 2. But the beauty of these WM terms is that it makes computing a determinant very, very easy. So what we can do is we can go down the first column when computing a determinant here. And this determinant is equal to just this determinant of this 2 by 2 up top. T e to the t, t plus 1 e to the t, e to the minus t, minus e to the minus t. And in this case, again, you can have a little bit of fun here, but this comes out to be minus 2t minus 1. Okay? So let's keep rolling. W2 of t. Again, the only thing that's happening is I replace the second column, because m is equal to 2 now. I replace the second column by 0, 0, 1. So I still get e to the t, e to the t, e to the t. Now I get 0, 0, 1. Then I still have e to the minus t, minus e to the minus t, and e to the minus t. Again, I'm going to compute my determinant by going down the second column. This 1 here, this actually leads to a minus in the determinant, right? So you might have to recall a little bit of how to compute determinants. But in this case, it's minus the derivative of the 2 by 2 matrix, e to the t, e to the t, e to the minus t, minus e to the minus t. And in this case, you just get 2. Okay, so you get the determinant of this little 2 by 2 is negative 2, and then the minus here flips that over. All right, we're rolling, right? Let's keep it going. We're having a great time here. Things are starting to become clear. Let's keep it going. So e to the t, e to the t, e to the t, t e to the t, t plus 1 e to the t, t plus 2 e to the t. And then this is W3, so the third column, again, is replaced with a 0, 0, 1. Again, you can compute this determinant. It's quite simple. It just gives you e to the 2t. So now you can see that we've computed all of the necessary components. And so you can put all of this back together. You can get the specific part just given by this piece right here. So therefore, the specific part of your solution, well, this is y1, e to the t, and then times the antiderivative of g of s, and then minus 2s minus 1, that's w1, divided by 4 e to the s ds. That is the Wronskian here, so right here, plus y2, and then times the antiderivative of g of s, and then times 2. So maybe I should, I'll put it out front, right? Because it's just a constant. I want to take it outside of the integral because it's not going to do anything. Although I will leave the 4 on the bottom just so that you can see the Wronskian part. And then the last piece of this, y3, the integral here, and g of s, still there, e to the 2t, 2s, it's inside the derivative, and then divided by 4 e to the s ds. And that will give you your specific part. In fact, if you do the antiderivatives and add c1, c2, and c3 to each one of those integrals, that will give you the full solution to the differential equation. So everything is there that you need. The only thing that's missing is a specific g to perform an antiderivative computation with. So if you wanted to, you could use g is equal to maybe e to the 3t or something like that, or any sort of g that you want to plug in there and compute some integrals. What I wanted to emphasize to you, though, is how to compute these things. Now, look at the active ingredient here. The active ingredient for all of this is Cramer's rule, right? So a lot of computation is hiding behind this. You might have to go back to your linear algebra course notes, remind yourself what Cramer's rule is and how we actually got to this solution. But for the purposes of this lecture, we can take this on faith for now, and we can use it in order to find solutions to these non-homogeneous higher order equations.